Great. So our final speaker of this morning will tell us about pipelines for the GMRT.
Okay, good morning. Good morning, everyone. So thanks to the organizers for giving me this opportunity to present this exciting work. So I'll be talking about automated radio data analysis pipeline for the uGMRT, which we call GARUDA, generic AI-based GMRT-tuned radio data analysis pipeline. It took more effort to figure out the name than developing the pipeline. But anyway, so these are the two main people who have been involved in developing this pipeline. Abhinav Narayan, who is a GRF student sitting there, and Atharva Mirasi, who is a PhD student, who is again sitting in the second row. So Abhinav did the heavy lifting of kind of developing most of the pipeline. Atharva also have kind of characterized the pipeline by analyzing many data sets. Okay, so this is the basic outline, and why we do need a pipeline, for example, at the first place. So if we look at the, there are growing challenges in radio astronomy, which is, with the advent of high-speed data processing and increasing capability of the telescopes. So the complexity of the data has been increasing day by day. For example, if you look at a radio telescope like uGMRT and SK, they generate a huge, massive data sets even like very small amount of time. When I was a PhD student, our data sets of full synthesis 8 hours data set would be like few gigabytes of data. Now the same has become now it's like 400 GB of data. It's like very difficult to handle. And this will keep growing actually, the computing power is increasing, and there are several scientific interests which needs more and more finer details into both in time and frequency domain. So this will keep growing. Data is often buried in under noise and RFI, so it's not very straightforward that you have some data put through a very basic pipeline and you will get the results. That's not going to happen. The situations around the observatories are keep changing, and they are making things complicated. And its radio data analysis is a bit complicated in a sense. It's not very straightforward. You have many rounds of calibration, flagging, imaging, deconvolution, and whatnot. So this area is also like is kind of developing over the time. If we look at the algorithms, if we look at the sophisticated deconvolution algorithm or imaging algorithms, they are also improving. So this complexity is being growing, and it will stay with us for some time. And the analysis process is of course non-trivial, as I mentioned. You take a normal data set and try to manually analyze the data set. Even like people like us who has like more than a decade of experience will take something like a few days to get around a good 8 hours data set coming from uGMRT, right? So this actually this already telling us that we need something better than kind of manually analyzing the data. So that demands the pipeline. And the second challenge, which is inevitable, which like the significant upgrades the telescopes are going on. For example, GMRT, which becomes uGMRT, it has gone from bandwidth 32 megahertz to 400 megahertz. VLA has gone from 100 megahertz to with JVLA 8 gigahertz and so on. And if you look at this data rate, for example, uGMRT, the data output is like about 400 GB for just 8 hours of data. Even I'm not talking about like 16K channels. This is like moderate 4K channels and 2 seconds of integration. So even GMRT can do uGMRT can do much better than that. If you look at JVLA, it produces something like 2 terabytes of data for 8 hours of observation. And better we not talk about SK, right? It will produce you like terabytes of data in a few seconds. How you are going to handle these things manually? Okay, you are not going to be able to do it manually, so you need some processing pipeline which will be really robust and will be able to take care of the complicated environment as I just mentioned, right? And then another challenge, which is the radio frequency interference, right? So this is, and I believe that this is going to be the next big challenge. Being even if you solve the all high data rate and processing and everything, you have your pipeline and everything, but this is going to make our life difficult. Gradually it will more and more difficult. It will make our life. So, for example, the growing habitats near observatories are causing increased RFI. We are making different types of communication devices and so on. Even if we look at the RFI environment at GMRT, when I started my PhD at L band and even band 4, it was like much better. But over the time, what happens is that habitat grows, people start using different types of gadgets, and they produce lots of RFI. So even if you go to secluded place like deserts or in North Pole, South Pole, but there are satellites in the sky which is going to give you tough time, right? So our algorithms must be smart enough to kind of work around this. And this philosophy is one of the main concern which we are trying to address in Garuda pipeline, right? So this is why Garuda is required. So this pipeline, there are quite a few, keeping all these things in mind, we have developed this pipeline, and this pipeline have a couple of salient features, which is like this pipeline is written in Python, mostly used. We have used CASA modules, which are robust. So because it is written in Python, it is in modular form. So it can be used as a single package if you want, or it can be used in modular form if you want to. For example, you have done the calibration, you just want to flag RFI using AI, so you can import this module separately, not a problem. Flagging and calibration has been done in, it has been done parallelized, so it can run fast on hardware capable, capable hardware. I mean, the most salient feature is that it has an AI-based method to reduce, and the AI-based method which can identify bad data, RFI, and which can basically does not require manual intervention to look into the data and kind of get rid of them. It is optimized to handle data which has like more than 50% RFI corruption. This part I will come. And this is scalable, and it is optimized for GPU. So you can actually kind of scale it for next generation telescopes like SK. So this is a basic flowchart of Garuda. We start with raw data, and then we flag dead antennas, which are like bad. Then we do a first round of calibration, remove some systematics. For example, if you have some gain drop, or some antennas has gone doing fluctuating stuff in middle, so you can get rid of those things here. Then you do a second round of calibration, and then separate the target source, and then you pass through this block, which is basically identifying RFI using both statistical method and ML based method, and then it produces a clean data which is flagged and calibrated. Then you go to the imaging pipeline. So this is again the same thing which I have mentioned in the last slide. Only thing is that this removing the strong RFI and all these things, we do use modules from CASA, and then we also have our ML and statistics based flagger, which we use in between. So it is like both we use CASA and our own developed module to kind of get the data analysis, right? So now, once you have this clean data, you can go for imaging. So to complete, Garuda, we do have two imaging pipelines, which one is like Continuum pipeline, which can do self-cal and Continuum, in an automated way. So this is called WISP. And then we also have a spectral line pipeline, which can do, which can generate spectral cube and moment maps, or in an automated way. Of course, you have to set up the parameter files. So this is called SLEEP. So with this, you can produce kind of good quality image. So why particular machine learning? Machine learning is quite an interesting tool in the era of the large data and so on. So machine learning enables precise analysis, of course, because it will identify the feature where you have RFI, and which traditionally, if you keep looking, so that is kind of cumbersome. Okay, while statistical methods also works good in cases where like your corruption is not moderate to minimal, and there the statistical method works fine. But when your RFI corrupts your data more than at 50% level, then all the statistics actually they get shaky. Because the primary statistics by which you determine the statistical property of good data, that gets corrupted, and it propagates to your determining data which is kind of bad. So this is a quite interesting part where Garuda really do well. So our deep model, which we have kind of trained and tested, so it works even with a 90% corruption. So if you have a data which is like really corrupted, like more than 60-70% corruption, it do kind of identify good and bad data. And this algorithm particularly has been implemented in GPU using TensorFlow. So it really can be accelerated if you have GPU in your machine. So it can work really fast, right? So for machine learning, what we have done is that we have first generated synthetic data for tuned for uGMRT, and trained our network to understand. For example, this is like one example. You have this is for one particular baseline, time versus frequency data, and this is simulated data. And we have infused, this kind of RFI, narrowband RFI. So the y-axis is frequency, and the x-axis is your time. And because we have put it in by hand, we know where the mask should be, right? So this is like one data set we have given to for training. This is another simulated data which has like a little bit more complicated environment of RFI. You have both broadband and narrowband RFI. Some is like persistent over the time. In some case it is not persistent over time. Some it is coming here, it is fending over here. This RFI, for example, it is localized in time and frequency. So this is another complicated environment what we have kind of given for train for Garuda. This is another one which is like mixed in both time and frequency domain. So after this, like we have trained, and let us see like how now it produces the results basically. So this is a real data set. This is a real data set for uGMRT, which is like one of our observation, Triangulum 2. This is for antenna C4, C6 baseline, and this is band 5, right? As you can see, there are a lot of RFI over here. Here, this portion is good data. And if you can notice it, so there is a gain fluctuation over this region from here to here, and if you can see it a little bit over from here to here, so there are some systemic issue was there, so the calibration cannot be done properly. And let us see whether Garuda can figure it out or not. So this is the same baseline time versus frequency plot. This is x-axis time, y-axis is frequency. As you can see, the the RFI, whatever, and the gain fluctuation, what it was. So Garuda could identify it and efficiently flagged it, right? So this is band 5. So we also have the observation for this guy, Triangulum 2 for band 4. So we have tested with Garuda. So this is a real observation. As you can see, this part of the band is completely kind of dominated by RFI. Here also you have RFI. There are short time range RFI coming and going, narrowband. So if we pass through Garuda, this is what you get. So it basically effectively picks out the region. As you can see, the beauty of machine learning is that it kind of chunks out portions from here, which are like localized both in time and frequency. So it's doing good. Band 4 is still better in a sense that the RFI environment in uGMRT, the band 4 is still better. Band 3 is a little bit worse, as you can see in this observation. So this is Triangulum 2, again the same galaxy, baseline C4, C6. And if we pass through Garuda pipeline, this is what you get. So this is quite encouraging already. I mean, it has been able to kind of pick up the and clean up the data quite efficiently. And to test the limit of Garuda, what we have done is that we have focused in one of the deep observation of of uGMRT, which is the field EGS deep field. So we have about like 350 hours of data in this field. So what we have done is that, so these are the PIs of this observation. The data is in public domain. Jasjit, Jairam, Nisim, and company who have done the observation. It's like 350 hours of L-band data. And we have only used 19 days of observation from that, which is about like 175 hours of total observation. So this amounts about 170 or 120 hours of on-source data, that is on the target data. So the total data size is about 4.2 terabyte. Now, if you go and try to analyze this data by hand, it will, certainly will take quite a long time. So what we have done is that we have used Garuda to kind of analyze this data, and this is one kind of example baseline. If you can see this EGS field observation, as you can see, there are a lot of narrowband persistent RFI, also broadband, and this is how it looks. If you pass through the Garuda, this is how the clean image, clean frequency versus time looks like. And for kind of little bit older people like me, we try to we like to look at the data in UV distance versus amplitude. There are lots of these RFI spikes, and you will not consider this is a good kind of clean data. So after you running Garuda, you see this looks quite nice. A lot of the spikes has gone out, and you can actually work with this data and go for imaging, right? So this is what we have imaged this data. So Garuda took about 72 hours, about less than 72 hours to process the data, in a sense that it has given us the cleaned and flagged and calibrated data in less than 3 days. And this we have analyzed in a kind of standard server class machine, not too hi-fi or fancy. And then we have actually proceeded for the imaging. Imaging took us some time because we were trying to understand, within our group also we were trying to develop this WISP pipeline. So as you can see, this image looks quite nice. The RMS is about 2.4 microjansky, which is quite encouraging. Nisim and company, so they have also analyzed this data and published this data. So they have also got a similar RMS of 2.4 microjansky, 2.4 or 2.3. So now if you see, so there are actually a lot of sources which may not be readily visible over this full field of view. If I zoom in, so this is the central part about 0.1 degree or so. So this is what you see, and you can see there are a lot of sources, and majority of the sources has flux density of about between 10 to 50 microjansky or so. So this is what you see. So which at 2 microjansky RMS is actually comes very nice, right? So which is quite interesting. And if you see this image, there are quite a bit of interesting sources here, and so I have just cherry picked a couple of those images. This is one of them. This is another one. This is another one, triple source. I don't know what it is. So this is also so it's what I'm trying to convince is that it's quite nice. As you can see, there are this faint probably double lobe radio galaxy. So and this is in the same. So this actually really working good. So I have also imaged like one of Abhinav's work. This is Abel 3376 field, which is a bit complicated field. This is a cluster, merging cluster. As you can see, there are 2 BCGs which has both like diffuse emission arc over here, and there is another BCG, and there is another source over here. So Garuda actually does the job pretty well, because if it is selectively flagging some short baselines or doing something, then it would be difficult to recover kind of these diffuse emissions. Okay. All right. So that is the continuum observation that we have tested. We have also tested spectral line observation. We did analyze some data, many data sets by now, but I'm just showing 1 or 2 galaxies over here. So left hand side, this is spectrum of UGC H1 spectrum of UGC 6438. As you can see, both manual and the pipeline is actually matching pretty much well. My apologies here, the convention like blue and red actually in opposite. Here the blue is from the pipeline and the red is manual. As you can see in this galaxy, UGC 7983, which is one of Atharva's galaxy, ultra-faint dwarf galaxy. So here the Garuda pipeline is actually recovering more flux than which is analyzed by manual ways. So far so good. And these are the moment zero maps, H1 moment zero maps for manually analyzed and analyzed by pipeline. So which actually looks pretty good, similar. In fact, pipeline recovers a little bit more flux than what we have got it manually analyzed. So this is another H1 absorption line in a frequency switching mode using uGMRT again, and 2232 plus 117. I'm just trying to tell you that this is, frequency switched observation is not a standard observation, but still we tweaked the pipeline and it has got an optical RMS depth of like 3 into 10 to the power minus 5. So this is one of the best RMS what we have got till now with uGMRT. So this is also telling that, okay, this pipeline is working fine. So what's next? So this pipeline now can be used to target like large data sets, working on large data sets. For example, we have kind of taken on a project which is called Garcia GMRT archival H1 data. So we have a lot of around like 500 plus galaxies in GMRT archive, which we are targeting as Garcia sample. And we'll be analyzing all these data, so about like 3,000 hours plus hours of observation. These data will be uniformly analyzed and will be looked at to address kind of the pressing questions in galaxy formation in the context of H1, right? Like galaxy dynamics and dark matter distribution in these galaxies. And this will be by far the largest sample of H1 we have in the community, right? So by far we have already analyzed 80 plus galaxies using Garuda for data analysis and SLIP for imaging, right? So H1 imaging, right? So this is work. This work is in progress. Abhinav, Atharva, and Saugata and other students are also involved in this project. So this is Garcia. I'm just showing a couple of moment maps what we have generated. So not only the H1 line, we also can look at large deep surveys which has been done using GMRT. For example, there are deep continuum survey, as I was mentioning. EGS deep field has already like 350 hours of GMRT data in band 5. We have deep to field, which is about 1100 hours of GMRT data in band 4. And Cosmos deep field, which has like about 525 hours of GMRT data in band 3. Now look at this data volume. Like this is about 15 terabyte, this is 60 terabyte, and this is 40 terabyte. Now even like downloading this data will be a challenge. Keeping them and analyzing, of course, it would be a huge task. But with this pipeline, it will make certainly the efforts will be more more easy. And we can do a lot of science with that. I'm pretty much sure that there will be a lot of exciting science coming up. And with this, I will stop here and take question. And of course, GMRT, my take on this is that with analyzing and handling this uGMRT data, uGMRT is still one of the best and fantastic instrument. You will get the RMS, which can do exciting science, and the future is bright, as I can see. Thank you.
Nice talk. So we've heard several talks just in this conference about different pipelines being developed for uGMRT, some at Indore and NCRA. Is there some effort on coordinating these efforts? So for the wide user community, it's a more unified pipeline that is visible. For example, it's not clear to me which of the pipelines are better or worse for what kind of applications and so on.
Right. So, okay. So, yes, I agree with you that there are many efforts. Actually, we are also within ourselves in communication, and we do interact. Different pipelines have different features. For example, Ruta has a capture pipeline, which also works great, using CASA. So, this AI-based flagging is the salient feature, which is not there. And in fact, if you are like, experienced enough using AO flagger, to flag kind of RFI and all these things, that also, do well. So our effort was to kind of, bring these together and, make it a streamlined process, which we have been working for some time now, 2.5 years. And yes, we are in talk, and we had a discussion with, of course, I mean, I'm a student from NCRA, so so you cannot say that, So yes, I mean, at some point you will have all these pipelines, and you can use it like as your data challenge, the challenge in the data. For example, if you have very clean data and you're already accustomed to it, kind of, using some pipeline, you're welcome, not a problem. Yeah, so this pipeline is not yet public. We are still testing some of the modules. So we are hoping that by the end of this year, this will come up for, So we are internally testing, actually. I mean, anybody, for example, within India, we are asking, like, if you want to use it, please use it. But we are still, because testing, we are not releasing it yet.
Okay, we'll take that question in the middle there and then come down to the front.
So is this pipeline tested for band 2?
Yes, I have used this pipeline to 2 data sets of band 2. So the band 2 RFI situation is it's a difficult, and you have a chunk of about 20 megahertz where you have to first split the data and run the pipeline. Otherwise, identifying RFI is not the problem. Problem is that it won't let you calibrate the data because of so much of kind of corruption. So yes, we have used it to download to kind of analyze. So 3 hours of band 2 observation, we got RMS of about between 2 to 3 milliamps. Yeah.
And just one whole follow-up question.
Yes.
Can it do direction-dependent calibration?
No, not yet. So that is like, one of our wish list, which would like to integrate with WISP, the continuum imaging pipeline. So that is not done yet. Yes.
Thanks.
Yeah, so thanks first for a very interesting talk. I have a couple of questions,
Yes.
and then a comment to follow up on the first question that was asked. But the unique thing, as you yourself highlighted, is the use of the machine learning for the RFI rejection. And I think you mentioned in passing that it's probably doing as good as AO Flagger or any of the other routines, but it's just that it goes through much faster than the manuals.
Yeah.
I want to understand what kind of machine learning algorithm is being used here, and are you running that on the GPUs in the sense that that algorithm was available with the GPU version, or you have coded it for the GPUs?
Okay, so we are using basically YOLO. This is CNN basically. It's a standard. The pack. I mean, look. If you look at the infrastructure, that is standard, and it uses TensorFlow, which can be implemented in GPU. We have not we have built the network, but we did not do any kind of this machine learning programming tweaking. No, so this is like standard. It can work on standard GPU. So you really do not need to kind of tweak or do anything. It's just the network and how this whole things is been arranged. So that is about it. And we have tested. We are actually using GPU, and our GPUs are like normal standard, like A4000, not very fancy one. And it can be scaled up, not a problem. It's a modular thing.
So it's a CNN algorithm which is already available to you in a GPU version.
Yes.
And you're just
Yes.
tweaking the parameters to get what you want.
Yes. So yeah. So this is the way Garuda is being written, is that you have an option to kind of switch off or switch on GPU. For example, you can run on your laptop with CPU. Then you have to switch off the GPU, which will still run, but it will take more time. Yeah.
Okay. And I'll just end with that comment that I fully agree that I think we should try to consolidate our
Yes.
efforts. We are not, we have few people working on these things.
I
It'll be
agree.
good to consolidate and try to
Yes.
get the best that's possible.
Yeah, absolutely. And I also feel the same, that it will actually, bring out the most of uGMRT observations actually. Yeah.
And we'll just take one last question.
Yeah, Ruta.
Hello. Yeah, thanks. I had a couple of questions, but short ones. I'll keep it short. So, like this machine learning flagging that you're doing, how, like it must be, sometimes it may also flag good data, for example. And the RFI situation or the nature of RFI also varies across GMRT bands. So how have you trained it to, or is a common training that you did based on simulation sufficient to apply it, sort of go for it across
Yeah.
bands, and what would be the validation?
Yeah.
And the other thing was in spectral line analysis, like recovering more flux, is that would you consider that as the success of the pipeline, or you would take it with I don't know,
Yeah.
pinch of salt?
Correct. So to answer your first question, it's a very interesting question actually. You are right that RFI environment actually changing. So this took us some time to realize. So first we were actually kind of training the network, just saying that okay, these parts are RFI. Then this environment keep changing, right? So the machine learning sometime will do good, sometime will not. Then we changed our strategy. Then we said that okay, don't look at the RFI, look at the good data. These are good data, these are masked. Try to identify that, because good data will have a uniformity. Okay, so then this actually worked. So instead of like training on RFI, and we train on where the good data. So it's instead of asking the question, try to find out RFI, no, look for good data. So it worked, and because the good data will have uniformity irrespective of the sources and other things, so that worked really well in my opinion. And to answer the second question of you, this we have actually looked. So this is because if you look at the H1 emission, this is a diffuse emission, right? So it really depends that how much flagging you are doing at the short baselines. So typically what happens if you are doing it manually, we look at this, oh, this looks bad, let's flag it, okay. So that is not completely optimized. So what Garuda has done is that it has kept, it has flagged what is required to flag. It did not flag what does not look so bad. So here for this data, we have found is that it actually kept a lot of short baseline, which otherwise in manual flagging we have actually flagged. So that is why in manual flagging, because of the, because we have lost this short baseline, then you did not, we were not sensitive to this diffuse emission. That's why in manual analysis, it picked up less flux, but in pipeline, it did, pick up good amount of flux. Yeah.
If we can thank the speaker again. And
Thanks.